And next up, we have presenting for Team UnWastewater. Please welcome Kelvin Green from Connecticut, who's studying civil and environmental engineering at Princeton University. Kelvin, welcome.
Thank you.
How are you today?
I'm excited.
Good. Well, welcome to Grand Rapids. The stage is yours. We're looking forward to your presentation.
Thank you so much. Hello, everyone. Thank you all for joining me here in Grand Rapids. My name is Kelvin Green, and it is my honor to be presenting to you on behalf of Team UnWastewater about our plans to revolutionize wastewater treatment through a novel technology called microbial electrosynthesis. First, let me quickly introduce our team. We are an interdisciplinary and multi-institutional group of undergraduate students studying biochemistry, material science and cell biology, computer science and mathematics, and civil and environmental engineering. Today, I hope to convince you all that domestic wastewater treatment is an industry that is ripe for innovation. Specifically, I aim to show that our current treatment technologies are inefficient and linear, that they are incredibly energy intensive, and are significant contributors to greenhouse gas emissions. Ultimately, this makes conventional wastewater treatment inconsistent with the United Nations Sustainable Development Goals and necessitates the use of new technologies like microbial electrosynthesis to circularize this industry. So what is wastewater? Generally, there are two forms of wastewater, industrial and domestic. We choose to focus on domestic wastewater because it is ubiquitous, and as a result, it represents the single largest untapped field for microbial electrochemical technologies. Prior to the invention of the activated sludge process in 1913, wastewater treatment was rudimentary, typically being dumped directly into waterways, and oceans, and streams. This had serious health implications for all people. And now we use the activated sludge process to treat wastewater. The way that this process works is typically with an aeration basin. This involves feeding wastewater to a high concentration of microorganisms, which then break down the wastewater into carbon dioxide, allowing the water to be discharged into the environment safely. The problem with this process is that it is incredibly energy intensive, representing around 3% of global electricity usage. In addition, the process directly emits greenhouse gas emissions and CO2 into the atmosphere. In fact, the Grand Rapids wastewater treatment plant emits between 3 and 13 tons of CO2 into the atmosphere each day. This is even more startling when one thinks about the energy content of wastewater. Specifically, wastewater contains over 10 times the amount of energy in its organic content than is necessary to treat it. This means that we are essentially using energy to dispose of energy. If that doesn't represent a linear take-make-waste system, then I really don't know what does. Our goal as UnWastewater is to circularize this process so that it is no longer inconsistent with the United Nations Sustainable Development Goals. Both the 2015 Paris Climate Accords and the International Panel on Climate Change have identified wastewater treatment as a critical industry to decarbonize if we want to meet our net zero carbon goals. But how do we do this? The technology that our team is researching is called microbial electrosynthesis. We believe that this technology has the potential to circularize the wastewater treatment industry by valorizing the organic content of wastewater into valuable chemical feedstocks. To understand what microbial electrosynthesis is, it's helpful to think of microbial electrochemical technologies, or METs, more broadly. This field was initially conceived of with microbial fuel cells, which is a technological platform that allows organics to be converted into CO2, and a reaction which releases electrons. These electrons can be harvested directly as electricity. Microbial fuel cells are the most mature microbial electrochemical technology, and several startup companies that we've spoken with, including Aquacycle and Cambrian Innovation, are pursuing their commercialization for industrial wastewater treatment. In addition, several wastewater treatment plants are experimenting with the technology to treat their high chemical oxygen demand waste streams. The problem with microbial fuel cells is that electricity isn't necessarily the most convenient product to be creating. This led to the invention of microbial electrolysis cells, which instead of releasing electricity, utilize the electrons that are generated to create hydrogen. This has been studied extensively in the scientific and academic literature, but there are several issues with the storage of hydrogen, and it's because it's even harder to store it safely. What's much easier to store safely are useful organic compounds. Microbial electrosynthesis uses this premise. Essentially, it involves capturing carbon dioxide released at the anode and converting it into useful organic products at the cathode of the electrochemical cell. This allows us to generate a number of value-added products, including ethanol, acetate, among many, many others. To pursue this project, we started working on a prototype. Our first model proved to be very inexpensive, but ultimately quite inefficient. So after consulting with mentors in academia, such as Professor Jason Wren of Princeton University and Professor Bruce Rittman of Arizona State University, we refined our prototype into a more modular, efficient cell. We undertook this work in the Princeton Wet Lab, and for this research, we were awarded an outstanding award at Princeton Research Day. And now we have a fully functional electrochemical cell that is currently undergoing microbial inoculation. This allows us to generate a number of products. Of particular interest is ethanol. Ethanol is an important precursor chemical in the pharmaceutical industry, and as a result, one can imagine using microbial electrosynthesis to circularize the production of pharmaceutical precursor chemicals, while at the same time reducing reliance on expensive aeration and environmentally damaging fossil fuels. Ultimately, we believe that this vision is much more aligned with the United Nations Sustainable Development Goals. And the critical advantage that I want to drive home today is that the microbial electrosynthesis platform provides great flexibility because it allows us to target the production of high-value chemicals. Currently, we are involved in research and development on our electrochemical cells, which we hope to scale up, which we intend to scale up to demonstrator-level reactors with wastewater treatment plant partners, such as the Scarborough Wastewater Treatment Plant and the Stony Brook Regional Sewerage Authority. Ultimately, we view this as a first step towards industry-wide integration of this technology. Our key partners in this process include academic and government funding agencies, biomanufacturing and wastewater treatment plants, and a number of indirect competitors, including Aquacycle and Cambrian Innovation, whose insights into the commercialization of microbial electrochemical technologies has proven essential as we have developed our own work. Ultimately, the value that this system has for wastewater treatment plant operators is it enables energy recovery in the wastewater treatment plant process, it reduces CO2 and greenhouse gas emissions, and it valorizes wastewater for offsetting residual wastewater treatment plant costs. Ultimately, the goal of UnWastewater is to shift the concept of a wastewater treatment plant from a treatment facility to a value-added biomanufacturing and resource recovery facility. The major strengths of this technology, as I alluded to, are that it enables the valorization of waste, and we've identified several opportunities for integrating this technology into existing treatment plants infrastructure, lowering barriers for entry and helping to facilitate facilities in meeting their CO2 emissions reduction targets. The main weakness of this technology is that it is new. As a result, there's a significant amount of research and development that still needs to be done into the optimization of microbial electrosynthesis systems. But nevertheless, wastewater treatment plants seem incredibly excited about the prospect of using microbial electrochemical technologies to valorize waste and meet their 2030 carbon neutrality goals. Ultimately, in the words of our esteemed Professor Jason Wren, who has helped immensely with mentoring this project, it is possible to realize a carbon-negative, revenue-positive wastewater treatment process. I'd like to thank the Kendall College of Art and Design and the Wege Foundation for hosting this opportunity. I'd like to thank all of our academic and industry mentors who have provided invaluable feedback to us throughout this whole process. And I'd like to thank all the judges and support staff here today. Your feedback and assistance in setting up this opportunity is invaluable. And lastly but not least, thank all our supportive friends and family back home. Thank you.
Thank you, Kelvin and team UnWastewater. We'll let the judges chat amongst themselves for a few minutes. In the meantime, I read that your team mostly went to high school together. That's incredible. Can you tell us a little bit more about that, how you all came together on this project, and what the inspiration is?
Yes, so we all met in high school. Well, most of us met in high school. And then we actually met in the robotics team. And so we had a lot of experience doing competitive competitions together and working on tight deadlines to finish projects. So it was, it came with like a natural synergy in terms of like working together on this project. I was the one who took a class with Professor Ren, who first got me interested in this technology. And then I sort of pitched the idea to everyone on the robotics team, and the folks that came with me here today thought it was a great idea. And they also have a wonderful amount of experience in a lot of the technical details that I didn't. So it's been a really great collaborative project and a great opportunity just to reconnect with people.
Good for you. It's incredible. And inspiring leadership as well, you bringing along your team members. What did you realize was one of your greatest accomplishments in this project? When did you realize, hey, we've got this?
You see, as an engineer working on, I was some of the prototype guy. And so generally, prototypes don't always go as planned. So maybe less of hurrah moments, but having a completed electrochemical cell in hand, like after 3 months of working on it, was a very rewarding, that was a very rewarding moment, I have to say. A lot of work left to be done, but it was great. It was great.
Incredible accomplishment. Well, congratulations to you and your team for coming this far. Thank you for coming to Grand Rapids as well. Judges?
Hi, thank you very much for the presentation. It was very, very impressive, and the technology seems really phenomenal. I have a question around what the role you plan to play in the whole business ecosystem. So you've developed the technology. Are you planning to license or lease or sell? What happens when the ethanol comes out of the technology? Are you relying on the wastewater treatment plant to sell that to the pharmaceutical industry? Or like, how does the flow of
sort of like where we fit
work?
into this?
Yeah, exactly.
Yeah. So really, I think there's like two kind of premises to like what constitutes like a circular economy business. I think that there are businesses that are in and of themselves circular in that they produce something that they can then recover and repurpose. What we envision ourselves more as is facilitators of a circular economy. So the wastewater treatment industry, as it stands now, is a pretty inefficient industry. It costs a lot of money. It's all subsidized by municipalities. And we see ourselves as facilitating partnerships between wastewater treatment plants and chemical precursor companies. So there's really no shortage of demand right now in terms of a need for, people want ethanol, people want acetate, people want these pharmaceutical precursor chemicals and precursor chemicals in general. But what's lacking is sort of, someone needs to be able to give treatment plants the technology and then basically sell and support. Sell the microbial electrochemical systems, and then act as basically maintenance staff for those specific systems. So that's kind of where we see ourselves, not so much as a circle unto ourselves, but sort of fitting ourselves into the economy and circularizing an existing industry, if that makes sense.
Just a follow-up. So you expect the wastewater treatment plants to then sell the outcome, the ethanol, the chemicals to those partners? You wouldn't be selling those?
Yeah, I think there's like, I suppose, two approaches. One, which is like what you just said, you would rely on the treatment plants to resell those to pharmaceutical or to chemical manufacturing companies. The alternative is like we act as an intermediary, purchase it from the wastewater treatment plants, and then resell to pharmaceutical companies. Whatever model works best is the one we'd pursue.
Yeah, just as a follow-up to that, I thought that was a great answer to the question. But you are actually engaged in the circular economy because you're producing something. You're actually producing a physical thing. So how are you developing that particular hardware and the logistics around it in line with the circular economy?
Yes. So this is actually something that you all can help with. So what we've been doing so far is electrochemical cells are pretty difficult to make. The materials are fairly expensive, but we've had to use subtractive manufacturing processes to create those. We want to switch over to additive manufacturing processes. I believe someone here works on 3D printing, but so essentially like working with 3D printers to build our electrochemical cells, which is much less wasteful than what we've had to do so far. So the hardware itself is sort of, so essentially like we want to be making this additively. We have to make it subtractively right now, but we're hoping to transition over to doing that. Does that answer your question or follow up?
I guess I was thinking more about what your business model was here on the hardware, because obviously it's, I'm guessing it's something that you physically put into the water and it operates like that. And are you looking at how you can recover those materials, the materials that you're using to actually produce this piece of machinery, this equipment? Is it developed modularly, in a modular way?
Yes.
All of those sort of design principles behind it.
Yeah. So in terms of design principles, Aquacycle, one of the startup technologies doing microbial fuel cells, actually does this very well. So what they do is they essentially have each of their electrochemical reactors is about yay big, like a shoebox size. And what they do is basically just put a bunch of them together in series. And that's quite beneficial because it's much harder to actually scale up the individual reactor to like facility-wide scale. So it's actually much easier to build a bunch of small reactors and just join them all up together. In terms of recovering the parts of the electrochemical cell, this is like a really critical thing that we want to research and a lot of people in the field are researching, because the anode of the electrochemical cell and the membrane in the electrochemical cell represent like 90% of the costs of the equipment. So if you can make those two pieces of equipment recoverable, you not only like circularize the system by reducing the amount of waste from like whenever you retire a cell, but you also like recover a lot of value from that. And so that's a critical part of like where research is right now actually, is looking into how to circularize those materials.
I have a question, Kelvin, over.
Yeah.
Yep. Great project. Could you discuss how do you add any time to the municipal wastewater treatment processing? And how much energy does your equipment consume?
Right.
I assume it has some.
Yeah.
Discuss that against the value of the output of
Right.
your high
So
items.
I'll start with the energy question first. Essentially you need to, for a microbial electrosynthesis system, you generate some electricity from your anode where you're breaking down the waste. But you also do supplement that with an external power supply. So this is an energy neutral process. That said, a lot of treatment plants, including Grand Rapids actually, do have anaerobic digesters which produce on-site biogas. So your electricity would generally be carbon neutral already. The other thing is, if you were to compare that to the aeration basin that is used in activated sludge process, the aeration basin is 60%, up to 60% of all energy use in the treatment plant. So as a sort of alternative to that, you see significantly less electricity usage in comparison. And then your first part of your question was sort of, can you remind me again? Sorry.
I don't remember. I think you answered my question.
Oh, okay. Wonderful.
I have a question. So you mentioned very briefly that phase 3 of your project will be about, at least in part, partnering with communities. So I'm curious about what factors will help your team determine like what communities you will partner with, at least in the beginning. I'm guessing you want to partner with as many communities as possible.
Yeah.
But,
Yeah. I think the first step is building like a demonstration reactor, proving to the industry that this technology works, that this technology is viable. And then once you can do that, I think it's about partnering with as many as you can. The benefit of valorizing products for wastewater treatment is that you're mitigating the costs associated with that treatment. And so a lot of communities that might say not have access to wastewater treatment because it's a very expensive process to do right now, would have the ability to build out infrastructure to do that. So this is like sort of, as I see it, you have sort of two parts. One bit is like retrofitting existing facilities, which is sort of the first step. And then once you do that, you can think about how can we build new facilities in places that don't have access to wastewater treatment right now, and like how do you make those facilities as sustainable as possible? So yeah, carbon negative and revenue positive being the objective there.
Yes, I have a question regarding, you have two kind of pollutants, organic and inorganic. So you get rid of organic through this one, because CO2 and different compounds, you get. What about heavy metals and other things?
Yes. So heavy metals are typically more of a problem in industrial wastewater. So industrial wastewater being like output from some industrial process. You can think of like, I think aluminum smelters have a heavy amount of water output. So it's less of a concern in domestic wastewater. It is a concern. It's not really the focus of this system. That said, there are like successive treatment steps. So we're really focusing on aeration treatment steps. Really you have like a settling tank, aeration, secondary settling with recycling to that aeration, that's the part of the system we focus on. And then after that, there is a nitrification, denitrification process that eliminates, say, ammonia and other nitrogen-containing compounds in the water.
Thank you.
Great work, Kelvin. Thank you so much, and thank you so much to Team UnWastewater.
Thank you.
Good. Enjoy the rest of your day today. Thank you so much. All right.